The rapid adoption of LLM-powered code generation has fundamentally changed how software is built, but verification hasn't kept pace. We're stuck with debugging tools that are either prohibitively expensive, requiring minutes of agentic reasoning and thousands of generated tokens per file, or they operate at a coarse function-level granularity that's useless for precise patching. This creates a massive bottleneck for both the safety of open-source projects and the actual stability of deployed systems. Today, we're breaking down a new architectural approach that cuts through this overhead. A lightweight, multitask LLM that performs line-level bug localization in a single forward pass, requiring just one generated token per file. This comes from a recent paper by Nikolai Rozanov at Imperial College London, and the technical execution is genuinely elegant. Instead of routing code through complex retrieval pipelines or forcing an LLM to chain of thought its way through a file, the authors treat bug localization as a parallel classification task. The core design takes a pre-trained code LLM, freezes its weights to preserve its original code understanding, and attaches a lightweight auxiliary decoding head directly to the final layer. This creates a multi-channel model. The primary channel continues next token prediction for code generation. The auxiliary channel takes the hidden states of every line in a file, aggregates them, and outputs a binary classification, bug or no bug. Inference is just a single forward pass. You feed in a file, the model processes it, and you get a per-line probability distribution instantly. No iterative refinement, no API call spam, no thousands of tokens. Now let's get into the heavy technical lifting, because this is where most prior line-level methods fall apart. If you've ever worked with LLM tokenizers, you know they don't respect source code boundaries. A newline character isn't always a standalone token. It gets merged with surrounding words, sometimes spanning multiple lines or splitting across token boundaries. Previous approaches often just assumed the token containing the newline represented the entire line, which is fundamentally flawed. The authors solved this with a custom token line alignment algorithm. It's essentially a two-pointer sweep over the tokenizer's offset mapping. It maps every token's start and end character indices back to the original source code, identifies exactly which tokens belong to which line, and builds a clean list of token IDs per line. This means the model can actually use multiple tokens to understand a single line, without getting confused by tokenizer artifacts or losing context. Once the tokens are aligned, the model needs to collapse them into a single representation per line. The authors experiment with 3 aggregation strategies: taking the mean of the token hidden states, taking the sum, or just grabbing the hidden state of the last token in the line. Surprisingly, the last token approach often performs best, which aligns perfectly with how causal language modeling captures sequential context. Those aggregated line embeddings then pass through a small feed-forward network with array LU activation, followed by a linear projection layer that outputs logits over a 2-token vocabulary: bug and no bug. During inference, they use greedy decoding and take the argmax. Interestingly, they found that a sigmoid activation consistently outperforms softmax across most setups. While softmax is standard for next token prediction, sigmoid's independent probability outputs seem to handle the inherent ambiguity of bug classification better, allowing the model to assign high probability to the bug token without forcing a strict probability mass constraint. Training this architecture requires a clever approach to handle scale and imbalance. Since the model processes entire files at once, the batch size is defined by the number of files, not the number of lines. This means the number of samples per gradient step varies wildly. To handle the severe class imbalance, where most lines in a file are perfectly fine, they implement a weighted binary cross-entropy loss. The weight for the positive class is calculated based on the validation loss and treated as a static hyperparameter, effectively pushing the optimizer to pay attention to the rare bug tokens without destabilizing training. They also fine-tune using LoRA adapters on the frozen backbone, which keeps the parameter count low, prevents catastrophic forgetting, and makes the whole setup highly reproducible. Let's talk numbers. They evaluated on Defects4J for Java and PyPiBugs for Python, plus a new out-of-distribution dataset they created called Bugs Eval. On the full-file, line-level setup, their multitask model with LoRA fine-tuning hits state-of-the-art performance among comparable setups. A 1.7 billion parameter model achieves a 16.3% top 1 accuracy and 39.5% top 5 accuracy on Defects4J. When they switch to a shorter context window to mimic function-level chunking, a 16 billion parameter CodeGen model hits a 71.4% top 5 score, which is directly comparable to expensive agentic systems like MemFL that use GPT-4.1 and take minutes to run. Meanwhile, inference for their method takes milliseconds. They also ran a classical supervised fine-tuning baseline, which completely failed to generalize, hitting 0% top 1 on the test set despite learning the training data perfectly. This is a stark reminder that naively fine-tuning an LLM to output bug lists just causes memorization, not actual localization. The ablation studies reveal some genuinely interesting insights. First, adding more layers to the classification head doesn't improve performance, which tells us the features extracted by the frozen LLM backbone are already rich enough for this task. Second, the PEFT approach significantly outperforms training just the decoding head from scratch, proving that even lightweight adaptation is necessary to capture the specialized feature vectors needed for bug detection. Third, the out-of-distribution evaluation shows that while the model's ability to recognize bug patterns generalizes well to unseen Python projects, catching every single bug becomes harder. This suggests the core semantic understanding of false transfers, but the edge cases require more exposure or broader context. This paper introduces a highly efficient, architecturally elegant solution to a problem that's been bottlenecked by computational overhead. By decoupling bug localization from generative reasoning and handling the tokenizer misalignment problem head-on, the authors have shown that line-level fault localization can be fast, precise, and parameter-efficient. The multi-channel paradigm also opens up a whole new direction for LLM research, training models to predict multiple distributions simultaneously without sacrificing their primary capabilities. Future work will likely focus on extending the token alignment algorithm to function-level boundaries, scaling to larger model sizes, and exploring how multitask heads interact with increasingly complex reasoning tasks. If you're working on AI-assisted debugging or efficient model architectures, this is a paper worth studying closely. Let me know in the comments what you think about multi-channel LLMs versus traditional agentic pipelines, and I'll see you in the next one.